1 mile below the Red Sea sits a lake that should not exist. Its own shoreline, its own tide line, its own waves, sealed inside the ocean surrounding it. Step into that water, and there is no coming back. Something down there is alive, in a way that may explain how life began and where it could be found. The first hint arrived over a century earlier, and nobody understood it at the time. In the 1880s, a Russian survey ship called the Vityaz lowered instruments into the Red Sea off the coast near Mecca and recorded something odd at 600 meters down. The deep water was warmer than the water above it. 60 years later, a Swedish research vessel named Albatross found the same thing again. Water that was both warmer and saltier than it had any right to be. For a while, the leading explanation was almost embarrassingly simple. Scientists assumed the heat came from the equatorial sun, somehow trapped at depth. It took until 1965 for anyone to publish a serious account of what was actually down there. Two British scientists, J.C. Swallow and J. Crease, aboard the research vessel Discovery, lowered instruments into the deep basin of the Red Sea and recorded water 2 kilometers down that was not just anomalous. It was extreme. In the area later named Discovery Deep, they measured brine over 44 degrees Celsius. A short distance away, in what came to be called Atlantis 2 Deep, later surveys would record temperatures climbing past 56 degrees, hot enough to qualify as one of the strangest hydrothermal environments ever found in any ocean on Earth. Swallow and Crease titled their paper plainly, "Hot Salty Water at the Bottom of the Red Sea." A modest name for something almost nobody at the time could fully explain. Decades passed before anyone actually saw what those early surveys had only measured from a distance. In 2020, a research team from the University of Miami's Rosenstiel School, working with the marine exploration organization Oceanic, sent a remotely operated vehicle down into the Gulf of Aqaba, a narrow arm at the northern tip of the Red Sea. At a depth of 1,770 meters, in the final minutes of a 10-hour dive, the vehicle's lights swept across the seafloor and caught something nobody on board expected. Lead researcher Sam Purkis later admitted the timing could not have been closer. The discovery came in the last 5 minutes of the dive the team had been allotted for the entire project. A lake. A real, self-contained body of water, roughly the size of a soccer field, sitting inside another body of water, complete with a defined surface, a visible shoreline, and a boundary so sharp it looked deliberate. Scientists call these features brine pools. Only a few tens of them have ever been documented anywhere on the planet. And the deeper researchers have studied them, the stranger, and the more important they have turned out to be. So what is actually holding that boundary in place? Why does a lake of salt water not simply dissolve into the ocean surrounding it? Density is the first part of the answer. Some brine pools stretch for kilometers, forming what amount to underwater rivers and lakes, complete with their own slow currents. Others sit only meters across, barely large enough to notice unless a submersible passes directly overhead. What every one of them shares is water so dense that it behaves less like ordinary seawater and more like a distinct, self-contained fluid, willing to hold its shape against the entire weight of the ocean pressing down around it. Brine pool water can be 3 to 8 times saltier than the seawater above it. Salt is heavy. The more of it dissolved into a given volume of water, the denser that water becomes, and dense water sinks. That is why the brine collects and pools in natural depressions on the ocean floor rather than spreading out evenly across it. The same basic principle that lets a person float more easily in the ocean than in a swimming pool. But density alone does not explain why the boundary stays so sharp. Pour salt water into a glass of fresh water, and it does not sit at the bottom in a neat layer. It mixes. So why does the same thing not happen at the bottom of the sea? The answer involves two properties: leaving the brine at very different speeds. Heat and salt both want to move from the warmer, saltier water below into the cooler, less salty water above. Heat, however, spreads through water roughly 100 times faster than salt does. It escapes first, warming the seawater directly above the brine and cooling the layer directly below it. That temperature shift causes the water just above the surface to rise, while the water just below sinks back down into the pool. The result is a self-reinforcing current that holds the two layers apart instead of letting them blend, a process oceanographers call double diffusive convection. The same imbalance is visible in far shallower brine features too. In the Salton Sea geothermal system in California, researchers first documented this layering effect decades ago, watching salinity increase steadily from top to bottom in a pattern that made no sense until double diffusion was properly understood. What holds a brine pool in the Red Sea, apart from the ocean around it, is the same basic physics keeping a shallow geothermal brine layered in the California desert. It explains why the surface stays so distinct. It does not, on its own, explain why the lake does not simply run dry, since salt is still crossing that boundary a little at a time, drifting upward into the sea forever. A pool with no way to replace what it loses should behave like any other puddle. It should shrink. Eventually, it should disappear entirely. None of the known brine pools have disappeared. Some have been monitored continuously since the 1960s, and if anything, several have grown saltier and hotter over that time, not weaker. So if the brine is constantly leaking away, what is replacing it? During the Jurassic period, roughly 170 million years ago, the Gulf of Mexico was a partially enclosed basin, cut off from the open Atlantic by a ridge of land. Millions of years later, the Mediterranean underwent something similar during what geologists call the Messinian salinity crisis, a period in which the sea was nearly severed from the Atlantic, and much of it evaporated away. The Red Sea has its own version of the same story, sealed for a time from the Indian Ocean by shifting tectonic plates. In each case, cutting a sea off from the open ocean starts a slow, brutal process. With no new water flowing in to replace what evaporates, the remaining water disappears over time, and what it leaves behind is not empty ground. It is salt. Thick layers of it, sometimes kilometers deep, laid down across the floor of a sea that no longer exists. Time buried that salt under new sediment, pressing it further and further down into the crust. And when those basins eventually reconnected to the ocean and filled with seawater again, they were left with an unusual arrangement: an open sea above and a vast reservoir of ancient salt sealed beneath it, kept apart only by a layer of sediment in between. In the Gulf of Mexico specifically, that buried reserve has a name. Geologists call it the Luan Salt, and it still underlies much of the region today, feeding brine pools that sit on the seafloor thousands of feet above it. That arrangement does not stay stable forever. As more sediment piles up above the buried salt, the weight begins to squeeze it, forcing it to shift, warp, and crack the rock layers above. Geologists call this process salt tectonics. Those cracks give seawater a path down into the buried salt deposits, where it dissolves the ancient reserves and forms an intensely concentrated brine. Warmed by heat from deep in the crust, that brine rises back up through channels called diapiers and settles once more on the ocean floor, replenishing the very pools that are losing salt at the surface. A team of geoscientists studying the Orca Basin in the Gulf of Mexico, publishing their findings in the journal Scientific Reports, documented brine actively flowing downslope from an exposed salt diapier at the edge of the basin into the pool below, an undersea waterfall made entirely of dense, sinking salt water. The basin itself stretches roughly 25 kilometers long and 6 kilometers wide, and the brine pooled at its bottom runs nearly 8 times saltier than ordinary seawater. Sitting at a depth of over 200 meters, a body of buried ocean still being fed from below, millions of years after the sea that made it disappeared. The NEOM pools that Sam Purkis and his team found in 2020 tell the same story on a smaller scale. Their main pool covers roughly 10,000 square meters, fed by 3 much smaller satellite pools nearby, all sitting in a natural depression, less than an hour's boat ride from the Saudi coastline. A stretch of seafloor nobody had mapped closely enough to notice them before. That endless cycle of ancient salt resurfacing is what keeps every brine pool on Earth alive. It is also what makes the water inside them permanently, unchangingly lethal. The shoreline told its own story before any instrument did. Around the edges of these pools, researchers have found the preserved remains of fish, crabs, and eels, some of them undisturbed for years. The same salt that keeps the boundary so sharp also keeps a body from decaying in the ordinary way, turning the shoreline into an open-air archive of everything unlucky enough to have crossed into the brine. Footage from a 2015 Nautilus Live expedition in the Gulf of Mexico captured a fish repeatedly dipping into a brine pool and pulling back, as though testing water it already understood to be dangerous. Blue Planet 2 later filmed a cutthroat eel that misjudged the boundary entirely. Within seconds of crossing into the brine, it was seized by violent convulsions, thrashing and knotting itself before struggling back above the surface. The mechanism behind that reaction is straightforward, however alarming it looks on camera. Brine pools are almost completely without oxygen, and the extreme salt concentration pulls water out of an animal's cells far faster than its body can compensate. Combine oxygen starvation with that kind of cellular shock, and the result is immediate and often fatal. Add elevated methane and, in some pools, hydrogen sulfide into that same water, and the brine stops being merely inhospitable. It becomes actively hostile to almost every form of life that evolved anywhere near the surface of the ocean. That same lethal stillness has a strange upside. Because nothing decays normally in an anoxic, hypersaline environment, and because storms and landslides leave undisturbed layers behind in the sediment below, Purkis and his team proposed using the NEOM pools as natural archives, timelines of tsunamis, flash floods, and earthquakes stretching back thousands of years, preserved in far greater detail than almost anywhere else on the seafloor. A place defined by death, in other words, has become one of the most precise record keepers on the planet. By any reasonable measure, this should still be one of the most lifeless places on Earth. No light, no oxygen. Water so dense, it resists mixing with anything above it. And yet, along the very edge of that lethal boundary, something is thriving. Dense colonies of mussels, some estimated to be many decades old, packed tightly along the shorelines of brine pools worldwide. Shrimp, snails, and small crabs shelter among them. Hagfish, ancient jawless creatures that predate the dinosaurs by hundreds of millions of years, patrol the margins, waiting for anything paralyzed by the brine to drift within reach. Researchers who studied Pacific hagfish physiology in 2010 and 2011 documented an unusual capacity for surviving without oxygen, in some cases for well over 24 hours at a stretch. Their thick mucus coating may also slow how quickly salt crosses into their bodies, letting them tolerate brief contact with the edge of the brine that would kill most other fish outright. What they have is a narrow evolved tolerance, built for exactly this kind of margin, rather than any true immunity to the brine itself. None of it explains where the actual energy is coming from, though. There is no sunlight here to power anything, and the water itself is loaded with the very things that make it lethal. No oxygen, high concentrations of methane, and in some pools, measurable hydrogen sulfide as well. On paper, it reads like a complete list of ingredients for a habitat where nothing survives. The answer sits inside the mussels themselves. Their gills are packed with specialized bacteria capable of converting methane, of which brine pools contain an abundant supply, directly into usable energy through a process called chemosynthesis. In return for the energy the bacteria provide, the mussels shelter and protect them from grazers and filter feeders. It is a genuine partnership, each side unable to survive here without the other. Built entirely around a chemical most marine life goes out of its way to avoid. Researchers have also begun isolating unusual bioactive compounds from the microbial communities living in these pools, some of them being studied for potential anti-cancer properties, a reminder that what looks like a death trap on the surface has already produced results worth studying far beyond marine biology. Sam Purkis, the University of Miami marine geoscientist who led the 2020 discovery in the Gulf of Aqaba, described the site during a live broadcast in blunt terms. It's an incredibly inhospitable environment, and yet somehow, life finds a way. An ecosystem running entirely without sunlight, powered by chemistry that kills nearly everything that touches it directly, is starting to look like a living fossil of Earth's very first age. A growing number of scientists now think that description might be closer to literal than anyone expected. In 1871, Charles Darwin wrote a private letter to his friend and fellow scientist Joseph Hooker, speculating about where the first living organism might have appeared. He imagined some warm little pond, rich in the right chemical ingredients, where the earliest building blocks of life could have first assembled. Darwin never published the idea. He barely trusted it himself. But the phrase outlived the man, and for the next century, it shaped how scientists pictured life's opening act. A shallow, sunlit pool struck by lightning. Darwin's letter helped inspire decades of experiments, trying to recreate that warm little pond in a laboratory. In the 1950s, chemist Stanley Miller ran electrical sparks through a sealed flask of water, methane, ammonia, and hydrogen, simulating lightning striking a shallow pool on early Earth. Within days, the mixture had produced amino acids, the basic building blocks of proteins, and for a generation of scientists, that result felt like confirmation that Darwin had guessed correctly. That picture began to change in 1977, when researchers exploring the Galapagos Rift aboard the submersible Alvin discovered hydrothermal vents on the deep ocean floor, surrounded by dense colonies of life, running entirely on chemical energy rather than sunlight. It was the first confirmation that life did not need the sun at all, and it reopened the question of where life's very first chemistry might have taken shape. More than a century after Darwin had first raised it in a private letter he was reluctant to publish, brine pools have added a second unexpected candidate. Earth's oceans, roughly 3.5 to 4 billion years ago, are thought to have shared three defining traits: low in oxygen, rich in methane, and extremely salty. Anoxic, methane-rich, and salty is also, almost exactly, a description of a brine pool today. Sam Purkis has put the connection directly. Our current understanding is that life originated on Earth in the deep sea, almost certainly in anoxic conditions. If that is correct, a brine pool may be one of the closest living approximations left on the planet to the conditions life first emerged from, a functioning present-day model of Earth's opening chemistry rather than a theory about it. If brine pools really do preserve something close to those original conditions, the next question reaches a long way past Earth's oceans. 2 moons in our solar system carry oceans of their own, hidden beneath miles of ice: Europa, orbiting Jupiter, and Enceladus, orbiting Saturn. Both are thought to hold liquid water sealed beneath a frozen crust, cut off from sunlight in much the same way a brine pool is cut off from it here on Earth. Both oceans are also thought to be salty, shaped by chemistry that, until recently, would have been written off as far too hostile to support anything at all. That assumption does not hold the way it used to. NASA's Cassini spacecraft, during its long survey of Saturn's moons, detected plumes of water vapor and ice erupting from cracks near Enceladus's south pole, spraying material directly out of the moon's hidden ocean and into space. Analysis of that plume material found salts and organic compounds consistent with a genuine subsurface sea, not just a pocket of trapped ice. Europa is next in line for a much closer look. NASA's Europa Clipper spacecraft launched on October 14, 2024, and is scheduled to reach Jupiter on April 11, 2030, after a journey of nearly 6 years and 2.9 billion kilometers. Once it arrives, it will begin nearly 50 close flybys of Europa, at times passing within 25 kilometers of the Moon's icy surface, its instruments shielded inside a radiation vault to survive Jupiter's punishing magnetic environment. Its task is narrower than a direct search for life, and in its own way, more foundational. To determine whether the ocean beneath Europa's ice could support life at all, the same basic question a brine pool answers every time a mussel bed survives another year in total darkness. Whatever the Clipper eventually finds when it reaches Jupiter, one thing is already certain closer to home. Every assumption about where life can and cannot exist keeps being overturned by places nobody thought to look twice at, including a lake sitting quietly beneath a sea that most people will never know is there. Thanks for watching. Don't forget to subscribe for more ancient mysteries and impossible discoveries.